morning. This video is going to go through all of the different gas laws and do example problems to show you how you can use the equations to calculate the answers. We are going to start with Boyle's law. So the important properties of a gas are going to be pressure, volume, the amount of gas, and then temperature. And so all of these different gas laws are going to look at how these four different factors are related to each other in some way, shape, or form. So in Boyle's law, we're actually going to be looking at the relationship between volume and pressure. So assuming that temperature and the amount of gas stays the same, Boyle's law basically states that an increase in volume, so making a space bigger, is going to cause a decrease in pressure. And think about it, that would make sense. Think about a syringe. If I have this much volume and a certain amount of pressure, if I decrease the amount of volume, I'm going to increase the amount of pressure. So volume and pressure are going to work opposite of each other. This is called an indirect relationship. Okay, so here's how Boyle's law works. The equation for Boyle's law is the pressure, the initial pressure, and the times the initial volume is going to equal the final pressure, or pressure 2, times the final volume. So really all you have to do for these equations is you just got to plug in the numbers. So let's read the example. A gas occupies 12.3 liters. Okay, that's the volume, so let's put that here, 12.3, at a pressure of 40.0 millimeters of mercury. So that's the pressure. So we'll put that here, 40.0. Okay, so 40.0 millimeter mercuries, 12.3 liters. What is the volume? So we want to find out volume, the final volume, when the pressure is increased to 60.0 millimeters of mercury. So now all I want to do is try and isolate this variable, right? So the first thing I'm going to do is I'm going to take 40 times 12.3, which is 493. Carry this down, equals 60 times the final volume. Now in order to get this volume alone on the side of the equation, I need to divide by 60, because that will cross that out on that side. Divide by 60. That'll give me 8.216. Let's see, we have 3 significant figures, so 8.22. This was in liters, so 8.22 liters. So fill in what you know, the pressures, the volumes, for initial and final, and then solve for whatever it is that you're missing. Piece of cake, right? Let's try the second one together. So if a gas at 25 degrees C occupies 3.6 liters, so here's our volume 1, 3.60, at a pressure of 1 atmosphere, put that there, what will be the volume? So again, we want to find volume, so we'll put that over here, at a pressure of 2.5 atmospheres. So take 1.0 times 3.60, that's going to give you 3.60, 2.5 volume 2, divide by 2.55, and the volume 2 is going to equal 1.44. Volume is being measured in liters, so 1.4 liters is what our final answer is. So fill in what you know and solve for what you're missing. You can also kind of check your work by thinking about what Boyle's law means. So for instance, we know that in Boyle's law, things move opposite. So if pressure increases, right, then volume's going to decrease, and vice versa. They're going to move in opposite directions. So just read the question. If a gas occupies, starting at a pressure of 1.0 atmosphere, if we're going to increase the pressure, then we need to think to ourselves, well, if pressure is increasing, then we know that volume is going to decrease then because they work opposite. And then check, well, we started with this volume, 3.60, and we ended up with a lesser volume, 1.44. So that answer actually makes sense. So it's kind of an easy way to kind of check your responses. All right, so we're going to move on to Charles' law. Charles' law is going to look at the relationship between volume and temperature. So we're going to assume that the pressure and the amount of gas, so of our four variables, pressure, amount of gas, volume, and temperature, if pressure and the amount of gas stays the same, an increase in volume is going to lead to an increase in temperature. So unlike Boyle's law, where it was an indirect relationship, when one went up, one went down, Charles's law is a direct relationship. When one goes up, the other is going to go up. Volume increases, temp increases. If temp decreases, then volume is going to decrease. So it's a direct relationship. Be careful when you are doing Charles' law equation problems that you are always using Kelvin for your temperature. A lot of story problems, math problems for Charles' law is going to give you a Celsius temperature and you will get the wrong answer. You need to make sure that you are converting any Celsius temperatures into Kelvin. And that's just taking 273 plus degrees Celsius to get your Kelvin temperature. So let's do an example of a Charles' law problem. Okay, here is the equation for Charles' law. So volume 1 over temperature 1 is going to equal volume 2 over temperature 2. Now, for these, you're going to cross multiply at some point in order to solve the equation. Okay, this is the easiest way to do it. All right. So the temperature of a gas chamber changes from 298, so that was our original temperature, right? 298 Kelvin, to 353 Kelvin. So that's our second temperature. So fill in the spots in your equation. The initial volume is 10.0 liters. We want to find out what the final volume is. So this is what we're looking for in this particular equation. So here's how you do this. When you cross multiply, you're going to take 10 times 353. You're going to multiply in this direction, right? So take 10.0 times 353 equals 298 times the final volume. So take 10 times 353, 3530, 298, V squared, or V final, so take that, divide it. And you're going to end up with your volume final, I keep saying velocity, but it's volume, as 11.845. Let's look at significant figures. We've got 3, so 11.8. And we are looking at volume. We use liters, so it'd be 11.8 liters. Your final answer. So remember, on these questions, like going forward, when you see this equal sign here, what you're going to want to make sure that you're doing is cross multiply. So you're going to multiply the top number on one side times the bottom number on another. And then, so like here, 10 times the bottom number on this side, this times the top number on that side. And put that on opposite sides of the equation. Let's try one more like this, just because I want to make sure you understand the cross multiplying process. If you feel like you got it, then you can skip ahead to the next gas law. So hydrogen gas contracts at a constant pressure of from 1.0 liters, so that's the top volume, to 0.95 liters, that's the final volume. The initial temperature is 20. Now remember, here you go, this is in degrees Celsius, but it has to be in Kelvin. All of these gas laws use Kelvin, so you would take 20 plus 273 in order to get, so that would be 293, your degrees Kelvin, so that was your initial temperature, to 93, and we want to find the final temperature. So cross multiply, 1.0 times temperature final equals 293 times 0.95. Multiply these across. So take 293 times 0.095. That's going to give you 278.4. 1.0. Divide. And your temperature final is going to be 278.4 0.4 Kelvin. So sig figs would only be two numbers. So to make this okay significant figure-wise, it would be 2.8 times 10 to the 10 to the second Kelvin. And then you only have, I'm not going to be super concerned about significant figures on these, but that would be technically your correct answer. 278.4 Kelvin, which significant figures would be 2.8 times 10 to the second Kelvin. Again, double check your work. You know, according to Charles' law, it's a direct relationship. So if temperature is increasing, volume is going to increase as well. Our volume actually decreased, so you're going to expect that your answer is going to be lower than the original temperature. We started at 293, we ended at 278, so that actually the answer makes sense. Gay-Lussac law is going to look at the relationship between temperature and pressure. Again, it's a direct relationship, so when temperature increases, pressure is also going to increase, and we're going to assume that the volume and the amount of gas stays the same. Question, a 30.0 liter sample of nitrogen inside a metal container at 293 K is placed inside an oven whose temperature is 323 K. Pressure inside the container was 293 K, was at 3.0 atmospheres. This is the pressure. What is the pressure of the nitrogen after its temperature is increased? So pressure number 1 is 3.0 atmospheres. Temperature number 1 is 293. Equals pressure 2 is what we want to find out, and temperature 2 was 323. It's all in Kelvin, so that's good. We're going to cross multiply, and so we'll get 3.0 times 323 because we're cross multiplying equals final pressure times 293. Do the math. 3 times 3.23 divide by 293 to get the pressure final by itself. And your final pressure is 3.30 atmospheres. Check the significant figures. Yep, got 3 atmospheres is what we started with for our unit, so that's what we're going to end with. And again, think about this to yourself. We increased the pressure, so we would expect that the temperature is also going to increase. We increased the temperature, so we would expect the pressure would increase. The pressure did increase. It went from 3 to 3.3, so our answer actually makes sense. So that's the Gay-Lussac's law, looking at pressure's relationship with temperature. Now what we're going to do is we're going to combine all of the laws together into the combined gas law, which combines Charles, Boyle's, and the Gay-Lussac law together. So we're going to put all of these into one handy-dandy equation. Here's the equation for the combined gas law. So let's, again, plug things in. A gas has a volume of 800.0 milliliters, so that's volume 1. So let's fill that in, 800.0. And 250 K temperature. 300.0 is the pressure torus. So 300.0 equals, we want to find volume, right? So volume, final volume will be over here. Pressure is 600.0 torrs, and the temperature is 500 K. So again, you're going to want to end up cross multiplying. I would do the math for these ones first just to make it a little bit more manageable. So 300 times 800 is going to give me 240,000. Here we go. Let's cross multiply. So 240,000 times 500 equals, oops, this should be, volume's final here, equals 250 times 600.0 b squared. So multiply these across, divide, go back and look at what units volume was in. It was milliliters, so you'd end up with 800 milliliters. You do significant figures, we would be 8.0 times 10 to the second if you wanted to make it right by significant figures. So basically we're taking all of the laws and we're combining it into that one equation. All right, next is Avogadro's law. we're going to look at the amount of gas, typically in moles, is going to cause a direct relationship with volume. So increasing the amount of gas will cause an increase in volume. So to do an example problem of this one, here we go. Here's the equation, volume over N equals the amount of gas. So let's see, we're starting with the 6.0 liter volume at a pressure, constant temperature, constant pressure. We don't need those numbers though. It contains 0.05 moles. That's our original volume. If an additional 0.25 mole of gas at the same pressure and temperature are added, what is the final total of the gas? So we want to add 0.25 to 0.5, so that would give us 0.75. And we want to find what the volume 2 is. Again, cross multiply, 0.5 volume 2 equals 60, or 6.0, sorry, times 0.75. Divide 9.0 liters. Which again, go back, we ended up adding or increasing the amount. We increased N, so you would expect then that the volume is also going to increase, and it does. It went from 6.0 liters to 9.0 liters. So our answer is at least trending in the right direction. Last law to really talk about is the ideal gas law. These are equations that are going to combine all four things. So the combined gas law just looked at pressure, temperature, and volume, but the ideal gas law is going to throw in the amount of gas as well. So looking at all four situations. There is a constant that used in the ideal gas law, and the constant that you will use will depend on the pressure unit. So if you are measuring in atmospheres, this is the number you're going to use for your R. And if you're measuring in millimeters of mercury, then you're going to use this number for your R value. So again, one quick practice problem. All right, so what is the volume occupied? So we want to know, we're going to look for volume of 5.03 grams. We're going to actually change this to moles. Sorry, that's a misprint. So 5.03 moles of oxygen 2. Okay, so that's our N. That's what we have. So 5.03. At a pressure of 0.998 atmosphere. So that's going to be on this side, 0.998. And we're going to be looking for V. If the sorry. So, and then temperature is 300 K. 301 K Kelvin. So, look to see, are we measuring in atmospheres or are we measuring in millimeters of mercury? We're measuring in atmospheres, so our R factor is going to be 0.0821. Do the math. Be in liters and significant figures, 3, so 1 point. So really, if you go by significant figures, it'd be 125 liters is your volume. The last equation that the text talks about is Dalton's law of partial pressure. This is a piece of cake, so basically says that the total pressure of a combination of gases is going to equal the partial pressures of all of the gases. So if you want to find out what the total pressure is of carbon dioxide, so carbon and 2 oxygens, you would find out what the pressure is of the carbons, what the pressure is of the oxygen. You'd add them together to get your total pressure. So all you got to do is add up all of the partial pressures. Make sure that you understand these equations. A lot of equations on your test, just like your content practice. If you have questions, make sure that you are contacting me to ask the questions that you need via Zoom, via email, whatever it is that you need. I'm here to help you with. Have a fantastic week.